We are recording right now, so welcome everybody to the regular Marine Robotics Club seminar. My name is Travis Moziki, and this week's seminar is going to be on C++ programming, revolving around a PID controller, as well as fundamental elements of a PID controller. So one of the things, I'm going to be back and forth between the whiteboard from the beginning of this seminar, and then we're going to move full on into the computer. Like literally, I'm going to enter into my computer. So let's start off with just, I'm not going to get very heavy into control theory or to a background on control theory. We did that last week. There's a great seminar online right now by Ivan Bertaska where we go into your stability, which really, I mean, the main thing in any control system is stability of the system. And he speaks about pretty much how you get there and what the considerations are, what your poles are, what your transfer function is. But we're just going to talk very briefly about frequency domain with respect to time domain, and about just what the steady state response of a PI, and a PID controller look like. You can eat that pizza, Don. So we've all dealt, I'm sure, with time response, meaning, you have some function, f of x is equal to y, something along those lines, right? So probably a better one is going to be f of x is equal to sine of x. So you have some oscillating function, right? And this is going to go on where this is x, this is y. So pretty much, and I'm sure everybody understands this, but as x goes towards infinity, this function is going to oscillate between positive and negative some amplitude. Now, what does that mean in the frequency domain? Well, this function has a frequency. It's going to be, your f is equal to 1 over t, which is your time period. So for this, it's going to be something, let's call the time period is 2 pi. So your f is going to be 1 over 2 pi is going to be your frequency. So now, if we converted this, and I'm not going to go into the hows right now, but if we converted this function into the frequency domain, what would that graph look like? Where this is going to be your just your f in hertz, and this is going to be, we're going to call this h of s. Well, this graph only has one specific frequency. It's only one sine wave traveling at one frequency. So you would just have a single point in the frequency domain. So now you can do things like Fourier transforms and other frequency domain assessments on this function, where really, let's say that now instead of a sine wave, we have a square wave. Kind of the idealized case. Well, this actually, when you do your Fourier transform, is going to have an infinite number of frequencies internally. It's going to be all of these different sine waves, an infinite summation that make this up, and that's not that one, but the great Fourier brought this into play. So now we have multiple frequencies. So, we're going to have maybe a frequency here, or here, here, and if my explanation here, I didn't give my regular disclaimer, I'm not an expert, but I'm working on it. So the way that I see this is, it can be a continuous function, but I also kind of think of it as a scatter plot, because that makes more sense to me, because maybe you have an amplitude that's traveling at a higher frequency, so that's going to be up here versus a lower amplitude with a lower frequency, which would be here. So what's a filter, right? So what's a low-pass filter? What's a high-pass filter? Well, what a low-pass filter does is it literally says if your frequencies are below a certain value, then it allows them to pass. And this is an idealized low-pass filter. So all that it's saying is that this now, instead of h of s, I'm going to call this a, and that's your gain. So if it's a unity gain, what it means is that, all right, all of these are equal to 1, and then here it's equal to 0. So what it's saying is if your frequency is below a certain value, which is your cutoff frequency, if it's below that value, then that frequency, that signal can pass. If it's above a certain value, well, that signal gets attenuated, aka it gets multiplied by 0. So that's, to me, what frequency domain, how it visually relates to time domain. And then inversely, of course, we could have something like a high pass signal where it's 0 and then 1, band pass, stop band, you got whole different layers there. So the reason why I bring this up is we're going to implement a low-pass filter on our PID controller. It's a moving average filter is the name of that variety. So now that, okay, so the next thing that I want to talk about is actually what a P looks like, what's a PI look like, and what does a PID look like, the frequency response of the system. Thank you, Bianca. My darling. All right, so now we've got. Is this really any better? I'm just kidding, Bianca. I'm sorry. This is spectacular. So you're the bomb. All right, so. Now let's say that we are giving our system, and real quick too, I guess it's worth it to note just kind of what a control system really, what like a system block diagram looks like. So you're gonna have some input into a system, and this is your desired state. And this is gonna get a plus sign, and this is gonna get a negative sign. So this is a summing junction. So you have some output of your system, and that output of your system is getting run back through. It's probably going to have some filtering going on for your sensor suite, and then it's going to come into the summing junction. So you have what you want, your desired, minus your actual. So this is going to be your error term. That error term goes into your control system, PID controller, sliding mode, robust, feed forward. You got all these options for controllers. Then that the control signal, the forces that you want to generate is what gets fed into then your plant or your system model. So it goes then after you send those forces through your model, it gets run back in, and that's how you have a closed loop system. It's a closed loop or feedback system. So now let's say that we have a unit step function input. So we're just going to drive this at 1, whatever, just some value. Well, a P controller where P is simply, it's proportional to the error, where if you've got a lot of error, you're going to have a lot of response. If you got a small error, you're going to have a small response. So it's going to, because at this point you have such a large error, it's going to try to get to that set point as quick as possible. So it's going to go and it's going to overshoot and it's going to come back down and then it's going to kind of oscillate for a while there. So one of the things that you'll notice is that this is called the rise time, which is how long it takes your system to get to the signal that you're trying to drive it at. And it's got one hell of a rise time. Like, that's really fast. Now, granted, you don't have anything to reference it to, but now check out the PI. So the PI controller, it's going to raise a little bit slowly, and it's going to have some overshoot, but it's not going to have as much, and it's going to oscillate a little bit, but then what it's going to do is it's going to settle exactly on your desired state. And that's a function of an integral term, where in the frequency domain, that integral term is going to cross out with your error. It's going to cancel with your error, and you're going to have zero error as the system time moves towards infinity. So now what's a PID? Well, a PID, it's going to have slower rise time still, it's going to have less of an overshoot, and then it's going to oscillate a little bit, and then it's still going to find the balance. It's going to find that zero steady state error because it's still got that integral term involved. So, all right, well, there's benefits of each one of these. Now, it's also a PID controller, in any form of it is going to be your bread and butter if you get into controls. It's one of those, it's more than 50% of controllers worldwide are a PID controller. If you start talking about getting into fine tuning, getting into higher level controls, control theory, control allocation, you're not going to be using PIDs anymore. You'll develop a PID as a control, and then you develop your other fancy control system to show how much better it is than PID, because any iteration of a PID leaves something to be determined. But that being said, so this has got a really fast rise time now, but it's got a lot of overshoot. So if you don't care about your overshoot, you just want to get there as fast as possible, just a P could do the trick. The PID has a really low overshoot, so maybe you have very strict margins where you can't operate faster or at a higher level than what your input is. Well, then you want to go with a PID because you're going to reduce that overshoot. And a PI is somewhere in between. It's got pretty good lead time, it's got pretty good overshoot, and most importantly, the steady state error is going to go to zero. So now one more quick thing about this, because this is going to come into play when you actually go about implementing a PID controller. So you're going to have KP is going to be times your error. Your KI is going to be times I guess it's really 1 over, it's times the integral of your error. And KD is the S. The KD is the derivative of your error with respect to S, just some arbitrary term. So how do you code these? Right? Like, how do you code an integral? How do you code a derivative? Well, you do finite approximations. I'll kill this one, but thank you, dog. I realized what you were saying. So you do numerical approximations. Now, an integral, if you just want to go ahead and you have some curve through space, if you want to find out what the integral of that is, it's the area under the curve. So, you do your Riemann sum where you just have this area plus that area plus that area plus that area, and you just keep on going. So the way that you do that is you just add your error to whatever your last error was, and you just keep on doing that. Now the problem with that is as time goes on, you're still integrating, and you're integrating forever. Well, you reach saturation of your system because now your KI, your I term is going to be so much larger with respect to your other terms because you've been integrating over this vast time period. So you have to implement something called an anti-windup feature. And pretty much what an anti-windup feature does is it says, well, if this is my set point, well, and this is my response, so you have two ways to do it. You can either not turn the anti-windup feature on until you get within a certain margin. Let's say, plus minus 3 from what your set point is, 3%. Or you can turn it off after you get within that plus minus 3%. Now, for my money, I'm going to turn it on when I get within that plus minus 3%, because the whole purpose of the integral term is that your steady state error goes to 0. So if you're turning it off once you get within that steady range, then what's the point of having it in the first place? So the anti-windup feature, you want to turn it on once you get within a certain range of what your set value is. And you also want to do things like reset it when you get a new set point. If it gets just over a certain value, just standardly reset it, because again, it's just if left unchecked, it's like a memory leak where it's just going to be filling up with just making this I term just bigger and bigger and bigger. And the derivative, well, that's just a rate of change. So really all that is now if we go back to what just kind of a little exploded view, well, the derivative is, it's this point minus this point divided by some time span. So you pretty much assume that you have constant time when you're doing this and just say, okay, well, my D term is going to be my most current sensor read minus the sensor read before that. And just kind of keep that one running where you need to have what your most recent one was and the one behind it. All right, that's pretty much what I'm going to do on the board. And now let's get into actually writing some of this code. So now originally this was going to be a seminar that was Linux based, that it was going to be a Linux platform running ROS and C++. But yeah, so it was pretty much, it wasn't going to work out to be able to record it and be able to actually present it. I would have had no way to hook up to this monitor. So it's Visual Studio running C++. Now, for those of you that have worked with ROS or know what ROS is, I'm going to reference ROS when I'm talking, but the code itself does not have any ROS parameters or ROS variables or anything ROS in it. If you wanted that code, I can also give you that because that's probably a better version. Input-output data stream in ROS is just incredibly easy. It's so easy to read in from a file, output to a file, runtime variables, and just a lot of stuff that is a headache with C++, let alone C++ in Windows. I had this great error while I was putting this together where I literally have a variable declared and I use it the next line and it's saying, hey, you didn't declare your variable. That took a little bit of time to debug. It was uninitialized, which is my understanding in C++, you don't need to initialize your variables. You can just use them. Like that's kind of one of the points of C++. But so, all right, C++. How many of y'all have coded a program in C++? Okay, so a couple of you. Harold, are you sure? I heard you only write in assembly. So there's a lot of differences between C++ and C. The main difference inherently is that C++ is object-oriented programming, OOP, object-oriented coding, OO, whatever you want to call it. There's other stuff, there's polymorphism, there's overloading operators and all this other fancy stuff, but the main, yeah, and just have no data types. But so, yeah, the main thing about C++ is that it's object-oriented. So what does that mean? Anybody got a good definition of what an object-oriented programming approach is?
It means you have objects.
Okay.
And the objects encapsulate like the functions that operate on them.
That's right.
So it has, like, this whole-
So you said the right word. So you have member functions. So the whole point with an object is that you have these member functions that are getters and setters, are really the right way to put it. What's up, Colin? So now let's say I'm going to just do a little bit of pseudocode where so now with this is a strawberry, this is a cherry scented marker. I'm so happy right now. So with object-oriented programming, you're going to have private data, and actually, I'm going to code this so that people can see it at home as well. Because I'm more familiar with Visual Studio. I thought about it, and I started doing it.
Like nice graphs and stuff.
I know, and that's really where I wanted to go with this, but that just was not in the cards for today. Actually, let's go. New file. So. Thought about that too. So this is an H file, and what you're going to have is something. Let's say that we wanted to make some object. right? So some object is going to be the name of the object. I'm just going to reference this just to make sure. So yeah, you're also going to want your includes. This is really just pseudocode. This isn't going to actually be code. So I'll get into includes and some of the other header files that you're going to need in just a moment. But pretty much the general idea behind a C++ object is you're going to declare a class called SomeObject, and then you're going to have public data, not public L, public, and you're going to have private. So your public data is going to be functions and data that programs external to this script can access. So let's say I have my class here, and now I come over to my main file, and I want to be able to call, so I had, so we're going to just call that to include it real quick. And then I could say SomeObject. So now I have this SomeObject in my script, and the public functions and data I can access inside of this script. So I could say, let's say now I have int on int, and I have int another int. So if I say the object dot int, unint is equal to 5, well, I can do that just fine. But if I say the object dot another int, you'll see that it's not showing up. I can't do it. It's is equal to 5. The reason why is because this is private data. Now you might be asking yourself, well, what do I care, public or private? It's a free world. Let me just give everybody my data and move on with myself. Well, it's defensive programming, and you want to move under the assumption that when you pass your code off, you wrote your code, and now you move on and you give your code to somebody else years later, that they're going to mess it up. They're going to try to do something they shouldn't do. They're going to break a function. They're going to do something that just is not the way that it's intended to do. So, especially with the state variables, and the state variables are really what you want to set as private data. It's stuff like, this is going to be a heading controller, so we want to keep that heading as private. I don't want it to get corrupted by some other function call, by some other program down the line. So that's why you keep, but now if it's a public data, maybe you just have some flag that's a public data, and you can check that in another program, or if you change that in another part of the program, it's not going to really affect the primary mission of your project. Well, if it has to be public, then make it public. And it's also, this is the sort of thing where it's sort of up to user preference, but if I can make a piece of data private, I'm going to make it private every time. So now, what does that mean? Because let's say that heading, right? So unint, let's say that I want to have that updated, and that has to be updated from someplace else. Well, how the heck do I update it? So you do that, or if I want to see it even, because I can't even output it to my terminal from this program because it's private data. So this is why you use getters and setters. And a getter will get that data, and a setter will set that data. So what I could do is say now, and your getters and setters are your member functions, and those are going to be public, so that they can be called outside of the scope of your project. So I could make a function called void, and it's going to be get another int, and I'm going to say void set another int. So come there, and I'm actually going to bump this up into there. And new item. So now what I want to do is pound include my sample.h, and let's see. So now I want to start to talk about this object. I want to start to declare what it is, and the first thing in C++, one of the other main difference with C and C++, you can have allocators and deallocators. Constructors and deconstructors are specific function calls, where instead of having to allocate or deallocate memory at use time like you do in C, you can just, when you want to create a function, you allocate memory there, and on the back end with a deallocator, when your program closes, it automatically wipes it from memory. So we'll say some object. Now the way that you declare a constructor is, it's just the name of the object with parentheses. I'm missing something. Come on.
Are you all the way up top? Do you need the IO stream?
Yeah, it could be it. Oh, well, I don't think so, because IOStream is included in the header file. All right, so
Go back. Did you declare it in
You
the
didn't
class?
declare it in the class.
Yeah.
oh, duh, thank you. So yeah, so the constructors you're going to also have to declare in your class, and you just do it.
You removed the colon from all the.
Thank you. So, man, it's been quite the day. So now you'll notice here.
Get another ant needs to return something. Void.
Yeah, I mean it could. It doesn't have to.
Set another ant also passed in something to set with.
We'll get there. So,
You could do get another ant passed by reference as well.
yeah. So this is how you declare your constructor and your destructor in C++. There's no return type, and the only difference is that one of them has the tilde. So now when I go here,
Also, you want to go over copy constructor as well?
no, I'm not going to go into copy constructors. There's a lot of C++ out there, but this is just a basic rundown on classes, so that in about 5 to 10 minutes when I jump into the control class, you're going to be we're going to be on the same page. So, what you could say is what you want to use your constructors for is the allocation of your private state data. So, and the initialization of it. So we have another int. So now in here I would say another int is equal to 2. Bam. And it's done. And also, you don't have to, but I think it's good coding practices is to use the this member function, or the this member. Yeah. So pretty much it's a pointer to the current object. And what's that mean? Well, so I have this variable, another int. Now this is a member of the object SomeObject. And now, but let's say I had some locally defined variable int some other int. Well, what this operator, I know it's tough to describe this pointer without using the word this. So this pointer here is a way of letting me know that it's a part of this object. Where this one now, if I come down here and I say, well, some other int is equal to 3, I'm not going to get confused and say, hey, is that a part of my private data? Is that one of my state variables? So I think it's just a useful tool to have. But so we have that. Now, what I could do is come to source, and now SomeObject, when SomeObject gets called, it's going to initialize another int is equal to 2. So now the same thing with some other object, or SomeObject, pardon me, the destructor. Now, in the destructor, so what do you have to put in the destructor? What do you have to deallocate? So this, another int, is just an integer, and an integer already has a built-in destructor. So I don't need to deallocate that memory in here. I don't need to do something like delete another int. It's redundant. So what, now let's say though that I had int pointer. So now let's say I have, let's mix that up. So let's say I had this integer, this pointer to an int. Well, and I want to allocate this dynamically, where I come here and I say int pointer is equal to new int. Well, now I have to deallocate that. Now I would have to come in here and say delete int point, whatever I called it. And the reason why is because I use the new operator, which is pretty much allocating memory at runtime. So if I allocate memory throughout the course of my program, I need to be tidy and clean it up afterwards. But we don't have any of that right now. So if you don't have anything, just leave it blank. No big deal. So now we have some object, and I want to declare get another int. And this is going to return an integer. So now the reason why we have this return type here is that I can say something. I can just do this. The easiest way is to just say return another int. Now, if I come over to my source, I can say cout the object dot get another int. Now this code will actually run this. So all of that is later on for the control code. That's just the same project. But you can see here the first variable, the first thing on that screen is 2, all the way on the top left corner of my terminal box. I don't know if you guys can see it. I don't know how the quality is up there, but so there's a 2 there, and pretty much the point in case I've now accessed my private data. If I wanted to then change that private data, I would do another function, void.
And then here you can actually like make sure it's like within the correct parameters.
Yeah.
Like what the value can be.
So exactly, you could do error checking, where
Let's actually pass in an integer.
I mean, you can do it a couple of different ways. Yeah, you can say int value and sample age is here, int value. So now you would just say another int is equal to value, and again saying something like that, where this dot another int is equal to value. So now what's happening is in my source code, I can come and say the object dot set another int is equal to 100 or 10. Now let's say though that I do make it 100, but to Harold's point, well, I only want it to be if value.
I don't want to return gold in case the doesn't fail or not.
Yeah, I mean, you can do a lot of things, but if value is less than or equal to 100, allow it, or less than or equal to 10, I keep on saying 100. Less than or equal to 10, it'll set else, whatever, set it equal to 10. It's equal to 10. But yeah, so you can also say, you could also do things like here you would have return true, and here you would have return false, and then you change this to bool, and you go back to your header and change this to bool. So now the point of this is, so now for this function, right? So if the value that we're trying to pass it is within whatever parameters we set, then it'll return true. And if it's outside, so I tried to pass it something that it doesn't like, it'll let me know. So you could say something like, now you could put error checking on here, where if not, the objects, if this isn't going to set,
Are they, outside?
yeah,
In the wrong place, that's either if, exclamation mark.
yep. Man. Teamwork makes the dream work. So, so now you can check and say, all right, if not the object, then see out, hey jerk, your values are garbage. Garbage.
If not, it's gonna say, well, why are you saying, why are you not using the same? Fucking using those mistakes.
So, all right. And just to show, hey jerk, your values are garbage. Nice. So now I've successfully built a computer program that insults me, and we're ready to move on. So.